Hello
The signaling
everybody, I
system
hope you are
course
doing
is
fine.
basically about the
I have
mathematical
received a couple
modeling
of
and the
queries
analysis of
regarding lecture number
signals and
4 and
systems.
5, and I'll be
And
answering those
in
queries in
last
next
couple
few
of
lectures.
lectures, we have been
Today we
discussing
are
the mathematical
going to
models
discuss
of
about the
some basic
classification
signals.
of systems in lecture
And in
number
today's
6.
lecture, we are going to discuss about the systems. A system is basically a mathematical model of physical phenomena, or physical process that relates the input-output relationship. Input sometimes also known as excitation, and sometimes we refer output as response of the system. And if x is the input of the system and y is the output, as shown in this figure, you can see x is the input of the system and y is the output, then the input output relationship can be written in this form, where T represents the system operator. The system operator is basically the function performed by the system. If system performs, for example, integration, then output would be y equal to integral of x. If system performs derivative, then y would be simply equal to derivative of x. Now system can have a single input and single output, but many practical systems have multiple inputs and multiple outputs. For example, the climate control system. In climate control system, you control the humidity, temperature and the pressure, and so you have 3 inputs in the system and you have 3 outputs. Similarly, there are many systems practically that exist that are called multiple input and multiple output systems. Now systems can be classified in many ways. The most generic classification is given in this slide. System can be described as continuous time and discrete time, and we can also refer to the system as memory and memoryless systems. Similarly, causal and non-causal systems, linear systems and non-linear systems, time invariant and time variant systems, stable systems and unstable systems, similarly feedback systems and open loop systems. And in next slides we are going to discuss each of these in detail. Now starting with the continuous time and discrete time systems, it's a very familiar classification and quite clear from the title that the continuous time system is a system in which the independent variable is continuous. It means the signal can be defined at any point in the time. That is called the continuous time system. On the other hand, a discrete time system is only defined at the discrete intervals of time. And naturally, every signal that exists physically is a continuous time system, but sometimes we discretize the physical signals in order to process it on the digital computer. Then the next classification is the memory and the memoryless systems. Memory here refers the energy storing capacity of the system. So a system is said to be a memoryless system if the output any time depends on only the input at the same time. That is called the memoryless system. So it means the system doesn't have capacity to store energy, to memorize the history. An example of a memoryless system is a resistor. The input of the resistor is the current and the output of the resistance, let's say, is the voltage. So according to the Ohm's law, the relationship can be described mathematically as V equal to I into resistance. So at any moment the voltage across the resistor can be determined by instantaneous value of the current. It doesn't matter what the past value of the current was, the voltage across the resistor would only depend upon the instantaneous value of the current. On the other hand, a system is said to have a memory if the output at any time of the system depends upon the current input as well as the past input output. It means the history. It has the capacity to store energy. A simple example for memory system is a capacitor, right? So the output of capacitor does not only depend upon the instantaneous value of the current, but also what was the output previously, right? It means how much the capacitor was already charged. So output in that case depends upon the current value as well as the history, right? So we say this system has the capacity to store energy, therefore it is called a system with memory. The equations for continuous time system contains differentiation or integration in memory systems, and in discrete time system it contains difference equation, it contains delays, right? Whenever in mathematical equation of the system an integration is there or the differentiation operation is there, it means this system has the memory, right? And in discrete time system, if you find delays or time advances, it means the system has memory, otherwise the system is memoryless. So these kind of systems are also called dynamic systems, and memoryless systems are most commonly known as the static systems. So many physical systems, and in fact all the physical systems that exist are basically dynamic systems, are systems with memory that has the capacity to store energy. For example, a motor is also a dynamic system, right? Because when you apply input to the motor, the output depends upon the previous output as well. For example, if you apply 20 volt as input to the DC motor, then it depends, the RPM at the output depends upon the previous input. For example, if you apply input from the rest position, the RPMs would be different, and if you apply 20 volt when the motor is already rotating at 2000 RPM, then the output would be different. So this is called, these type of systems are called system with dynamic systems, and the mathematical model of these kind of systems contains integration and differential equations. Now in these examples we are given some mathematical equations, input-output relationships. In all these examples, x of t is input and y of t is output, and we have to identify which of the following systems are memory and memoryless systems, right? So as I told you, those systems which have differentiation or integral operators in their equation are memory systems, otherwise they are memoryless systems, right? So let's start with example A, this one. In this equation you can see there is no integration and differentiation, and y of t only depends upon the instantaneous value of x of t, right? So this system is basically memoryless system. Similarly here, y of t depends upon the instantaneous value of x of t, so this system is memoryless as well. However, in this equation you can see we have a derivative operation, and y of t does not depend only upon the instantaneous value, also the rate of change of the x of t as well, right? So this makes it the system with memory. It has the capacity to store energy. Similarly, in this equation you can see x of t does not only depend upon the y of t does not only depend upon the instantaneous value of x of t, but also the past value of x of t as well as the future value of x of t. Therefore, this system. So now the next classification is causal and non-causal systems. A system is said to be causal if its output at any time, let's say t equal to t naught, depends only on the input x of t for t less than or equal to t naught. So what does it really mean? That the output depends upon the current value of x of t and the past value of x of t less than t naught, right? So the output of the system depends on the current value of x of t and any past value of x of t, right? So that is the output of a causal system at the present time depends on only the present or the past values of the input, not on its future values. Right? So a system which output depends upon the present value of input and the past value of input, that system is called a causal system. And the non-causal system is that system which is not causal. It means the output of non-causal system would depend upon on the future as well. So all memory systems are causal because their output depends upon the instantaneous value of input. Again, there are few examples, few equations of the system given, and we have to identify from these equations, from these mathematical models, which of these systems are causal and non-causal. For example, starting with A, y of t is equal to x of t minus 1 plus x of t. Now in this equation we have x of t, which is the present value of x of t, and x of t minus 1 is delayed value of x of t. Therefore this system is causal. Similarly, here in this equation you can see y of t depends upon x of t minus 1, which is the delayed value, past value of x of t. However, this value x of t plus 6 is the time advanced value, it is future value. Right? So we can say this system is non-causal. And in this equation you can see that the y of t depends only on the instantaneous value of x of t, the present value of x of t. So this system is causal, and also this system is without memory. It is also static system. Now the next classification, a very important one, is the linear and non-linear systems. And linear systems are basically defined by the principle of superposition. A system is called linear when the independent variable and the dependent variables are linearly related. So all the linear systems basically follow the principle of superposition. So let us consider the system as shown in this figure, where x is the input and y is the output and t is the system operator. If the operator t satisfies following two conditions, then the system represented by linear operator t is called a linear system. And what are these conditions? First, the additivity, and other is homogeneity, or it is also called scaling property. So it has to satisfy additivity property and homogeneity property. And now let us discuss both these properties individually in next slide. In order to understand the additive property, let us consider two inputs x1 and x2, which are applied to a system separately. When x1 input is applied, let's say the output produced by the system is y1, and when x2 input is applied, the output produced by the system is y2. Now if both the inputs are applied combinedly like this, x1 plus x2, then output would also be simply the sum of the individual outputs, y1 plus y2, and this is called the additive property, and all the linear systems must satisfy this condition. And homogeneity or the scaling property is simply when input x is applied to the system, the output produced by the system is y, and when that input is multiplied with some constant value, let's say a, then output would also be multiplied with that constant. Now all linear systems must satisfy these two conditions, and actually we can combine these two conditions, and the combination of these two conditions is called the superposition property. This equation, we apply two scaled inputs, x1 scaled a1 times and x2 scaled a2 times. The output would also be scaled by a times. Now again we are given some mathematical equations describing the input output relationship of certain systems, In all these examples, x of t is the input and y of t is the output, and from these equations we have to determine whether the system is linear or not. So in order to check the linearity of the system, we will apply the superposition property. We will check the superposition property of the system. So how we can actually check the superposition property? We will check the scaling and the additive property, right? So starting with the example number 1, example number A. In this example, we are given the input output relationship of the system by this equation, and we are going to check whether the system is linear or not. So in order to do that, let us consider two inputs, x1 and x2, which are applied to the input of the system, and the corresponding outputs would be y1 of t would be equal to t x1 of t, and similarly y2 would be equal to t into x2 of t. Now these two inputs are combined, scaled and combined together and applied to the input of the system like this. And let's say the output produced after applying the scale and combination of these two inputs is y3 of t, right? So ax1 of t plus bx2 of t are applied together to the system, and t here actually represents the function that system performs. It's the system operator. So the function that system performs is basically it multiplies t whatever the input is applied, right? So here the input applied is ax1 of t plus bx2 of t, then this input would be multiplied with t. This is the output of the system when x1 and x2 are scaled and combined together and applied to the system. So y3 is equal to atx1 of t plus bx2 of t. Now in previous slide we calculated the output y3 of t with the linear combination of inputs, and the result is represented by this equation. Now let us find out what happens when the two outputs are linearly combined like this, where two outputs y1 and y2 are scaled and combined together, and here with the same scalar functions that we use in linear combination of inputs, which are a and b respectively. So replacing the values of y1 and y2 given in previous slide, we get exactly the same result which is produced after the linear combination of inputs. So this indicates the system is. Now similarly, another linear example is given, and I am directly jumping to example number D here, and other examples are very similar to the example A. You can give it a try, and if you find any difficulty you can ask. So in example number D, we are given the relationship between the input and output by this equation, right? And we have to determine whether the system is linear or not. And from the equation it looks like it's a linear system, right? In fact the equation is the straight line equation, y equal to ax plus b. Now let's see whether it satisfies the superposition property or not, right? For this, let us consider two inputs, x1 and x2. The corresponding outputs are y1 equal to ax1 plus b and y2 equal to ax2 plus b. Now let's find out the output of the system with the linear combination of inputs, right? When two inputs are scaled and combined together and applied as an input to the system. So the linear combination of inputs ax1 plus bx2 produce this equation, right? So the system, the function performed by the system is that the input is multiplied with a and then added with b, right? So here input is ax1 plus bx2, so that input would be multiplied with a and then added with b, right? So now simplifying this equation further would give you this result. Now let us find out the result produced by linear combination of outputs. So let's say y1, y2 are multiplied with a and b respectively and then added together. So replacing the values of y1 and y2 in this equation, value of y1 is ax1 plus b, and value of y2 is x2 plus b. And after some simplification, you can see that this equation, this value is not equal to this value, right? So this indicates the system is not linear, although the equation looks linear. But let me tell you another property of the linear systems is called the relaxing property, relaxed system. A system when input is 0 should have 0 output, right? For example, in this equation, if x of t is 0, y of t would be equal to b. It won't be equal to 0. So it is called not relaxed system. Linear systems are always relaxed. Relaxed means when input is 0, output should be 0 as well, right? So we can, since the system is not relaxed, therefore it is not linear. And if b was 0, then you can see that the output would be exactly same. Now the next classification is the time invariant and time varying systems. Time invariant systems are those systems whose characteristic doesn't change with the time. Right? The output may vary. Some students get confused sometimes that output is changing, it means the system is time variant. Now output may vary because input is changing. When the input changes, the output changes as well. But the time invariancy is basically the characteristics of the system that doesn't change with the time. The equation of the system, right? The equation of the system remains same whatever the time is, right? Then the system is called time invariant. And when the equation changes, the characteristics of the system changes with time, then the system is called time varying system, right? So a system is called time invariant if a time shift or delay or advance in the input signal causes the same shift in the output signal, right? Mathematically, if x of t is the input and y of t is the output, then delaying input by t tau units, for example here, would produce the same delay or time advance in the output. If the system satisfies this property, then so in this example we have to determine whether the given system is time invariant or time variant. We are given an input output equation where x of t is the input and y of t is the output, and it's quite clear from the equation that the system is time variant, right? But let's see, let's apply the test which we discussed in the last slide and see whether it satisfies the test or not, right? So that test is basically, we'll first introduce time shift in the input and we'll compute the output, and then we'll introduce time shift in the output and then we'll compare both the results. And if both the results are same, then system is time invariant, otherwise not. So let us first introduce the time shift in the input and compute the output. So let's say the output in that case is y1 and the time shift is introduced tau units, right? So input now is xt minus tau and output is y1 of t equal to x of t minus tau cos omega t. Now let's introduce same amount of time shift in the output. When same amount of time shift is introduced in the output, then the equation now can be written in this form: x of t minus tau into cos omega t minus tau, and you can see clearly in both cases the equation is different. Therefore the system is time variant. It is changing with time. It depends upon time. So in equation, if the time explicitly is involved, then system is called time stable invariant, otherwise system which produces bounded output when a bounded input is applied. So here the bounded input is represented by this expression and bounded output is represented by this expression. So bounded input means the magnitude of the input remains within the defined boundary, for example k1, right? For example, a unit step input is applied, right? So unit step input is a bounded input because its magnitude remains 1 throughout the time, and the output produced by the system should also remain constant within the boundary, right? It may amplify the output or it may attenuate the magnitude, but output should not increase with time. Either it remain constant or decrease with time. So that is called the bounded output. So here the bounded output is defined by this expression where y is the output and the magnitude of the output remains within the defined boundary k2, right? So when input is bounded input is applied to a system, a stable system, then output produced by the system would also be bounded. It would remain within the limits, right? And if it doesn't, then the system is called unstable system. A special class of system of huge importance are the systems which have feedback, right? So feedback systems are basically systems in which the output is fed back to the input, as shown in this figure. Output y of t is fed back to the input and it is compared. Feedback systems are very widely used in everyday life in many applications, and we'll be discussing these systems in detail in next lectures. Now in this exercise problem we have a capacitor connected to a current source. The current source is value I of t, the capacitance of the capacitor is C, and the voltage drop across the capacitor is Vc of t. The input output relationship of the capacitor is given by this equation, Vc of t equal to 1 upon C and the integral of current from minus infinity to d. We have to determine whether this given system is memoryless or it has memory, whether it is causal or non-causal, whether it is linear or non-linear, whether it is time invariant or time invariant, or it is so starting unstable. With the first part, whether it is memoryless or it has memory, quite clearly you can see from the input output relationship contains integral, right? And whenever we have integral or derivatives in the equation, the system is memory system, right? So from input output equation it can be seen that the output Vc of t depends on the past and the present value of the input. Therefore the system is memory system, it has memory, it is not memoryless. Now similarly, coming to the part B of this problem, whether the system is causal or non-causal, quite clearly the output depends on present value and the past values only, minus infinity to t, not minus infinity to plus infinity, but from minus infinity to t, right? So the output depends only upon the past value and the present value. Therefore the system is causal. Now coming to the part C, whether it is linear or non-linear. So for linearity we have to apply the linear combination of inputs, which is I1 of t and I2 of t. Let's say these are two inputs. When these two inputs are applied, the corresponding output produced are Vc1 of t equal to 1 upon C integral of I1 of t from minus infinity to t, and Vc2 of t equal to 1 upon C integral of integral of I2 from minus infinity to t. Now the linear combination of two inputs produces this result, right? So here the two inputs are scaled and combined together, and the function performed by the system is simply integral and multiply by 1 upon C, right? So these two inputs are integrated from minus infinity to t and divided by C, or you can write down this equation in this form by separating I1 and I2. Now let's see what linear combination of two output produce, right? So A Vc1 of t plus B Vc2 of t is equal to A Vc1 of t is equal to this, and Vc2 of t is equal to this. So in both cases we can see that the result is same, right? So linear combination of inputs produces the same result as the linear combination of two outputs. Therefore the given system is linear. Now coming to the part D, time invariancy, right? So in order to check the time invariancy of the system, we have to delay input by t naught units, right? So when input is delayed by t naught units, then input can be represented as I t minus t naught, right? So let us rewrite the equation, input output equation, by delaying the input, which is Vc1 of t equal to 1 upon c minus integral of I1 t minus t naught from minus infinity to t, and it is equal to Vc t minus t naught, right? When input is delayed by t naught units, output would also be delayed by t naught units. Similarly, when output is delayed by t naught units, it would produce the same result, right? Minus infinity t minus t naught. So ta here is basically t minus t naught. So either the output produced is same. Therefore we can say the system is time invariant. Now coming to the part E, whether the system is stable or not. For this we have to apply a bounded input. For example, we are applying a unit step input to the system, which is a bounded input, right? It is an input having constant amplitude, which is equal to 1. So when this bounded input is applied to capacitor, then what happens to the output? The integral of u of t, integral of unit step function, is basically the ramp function, right? So now current is constant, current I of t is constant, so u of t would be simply equal to 1, and integral of 1 would be t upon c, which is the ramp function, right? So ramp function is basically not bounded, it is unbounded because it increases with time. So when a bounded input is applied to capacitor, the output is unbounded. Therefore we can say the system is unstable. Now here another similar example is given, in which we are given a system in which the input output relationship is given by this equation, where x of t is actually input and y of t is output, and this is actually the block diagram of a mixer, an audio mixer. For example, when audio signal x of t when audio signal x of t is mixed with a sinusoidal waveform, right? We usually do in amplitude modulation, right? So we have to determine whether the system is memory or memoryless, causal, non-linear, linear, or time invariant, or stable and unstable, right? So give it a try, and obviously I will provide you the solution, and if you find any difficulty, you can always contact me. That is my end of email address. Lecture number 6 and 7, and a lot of exercises are given in the books I have referred to you regarding this lecture. Try to solve the exercises given in this lecture slides, or also in the books I have referred to you, and if you find any difficulty, you can contact me using my email address. Thank you very much.